Good morning, good afternoon, good evening, wherever you are. Welcome to the SNIA Networking Storage Forum, NSF webcast, extending RDMA for persistent memory over fabrics, actually also known as remote persistent memory or RPM. This is a live webcast here, and we are excited to bring you today Tony Herson from Intel and Rob Davis of Mellanox. By the way, this is John Kim, Chair of the SNIA Networking Storage Forum, and I'm happy to be your host and MC today. But the stars of the show today are, of course, Tony and Rob, who will present what's new in persistent memory for over fabrics, or again, RPM. So just a few facts about SNIA. So SNIA is an exciting organization all about storage, networking, and storage technology. Over 170 member organizations, over 3,500 contributing members, and over 50,000 total IT end users and storage pros worldwide are involved in SNIA. Learn more at snia.org/technical, or follow us on Twitter at SNIA, or follow the NSF at SNIA-NSF. A short legal disclaimer and notice. This material is copyrighted by SNIA unless otherwise noted as copyrighted by someone else. Member companies and individual members of SNIA may use this material in presentations and literature under the conditions that they use the material without changing it, and they acknowledge that it is, in fact, from SNIA. This is a SNIA project. None of the authors or presenters or myself as a host here are attorneys, and nothing in this presentation is intended as legal advice. If you need legal advice, please consult your attorney or corporate counsel. All right, that said, with the important disclaimers, and there are other important things mentioned on this slide that you should read, we will now go ahead and let's start out with what is persistent memory, why is it important, why is it becoming more popular, what is RDMA, and why do we need to extend RDMA? So with that, let me turn it over to Rob Davis.
Good morning. Thank you, John. And thank you to SNIA for this opportunity to talk about networking persistent memory. According to Wikipedia, in computer science, persistent memory is any method or apparatus for efficiently storing data structures such that they can continue to be accessed using memory instructions or memory APIs even after the end of the process that created or last modified them. What a mouthful. I think they left out after a power cycle, but maybe that is what they meant by end of the process that created it. In any case, for this talk, we are talking about DRAM or NVDIMMs and new persistent memory technologies like the highly publicized 3D crosspoint. These technologies sit between DRAM and hard drives and SSDs on the cost versus performance versus capacity line. They are faster than SSDs, but not as fast as DRAM. But they are less expensive than DRAM. They are also more dense than DRAM and can be accessed by not only the DDR interface, but sometimes over PCIe. Since persistent memory is persistent by definition, like a disk drive or SSD, it can obviously be used for storage applications. But there's one, since many storage applications use network connections for features like fault tolerance or high availability, the need to network persistent memory becomes a requirement for using those kind of applications. But there's one major problem with networking persistent memory, and that is that it's very fast, roughly 100 times faster than even SSDs. Notice the units on the persistent memory column on this chart, and they're in nanoseconds, and the NAND column is in microseconds. So basically an order of magnitude difference in performance. So we need to tweak. So if we look at how we might network these technologies, even the new networking technologies designed for SSDs like NVMe over fabrics are challenged by RPM or remote programmable memory. So we need to tweak these technologies, somehow optimize them to the performance levels needed for persistent memory. There are many applications that could take advantage of network persistent memory, so there's a lot of motivation to do this. As John said, remote persistent memory, or RPM, is the new acronym. Our industry loves acronyms. One example of an application that can take advantage of remote persistent memory would be in-memory databases. Remember, persistent memory is more dense and less expensive than DRAM, but almost as fast. So it fits this application space very well. And because it's persistent, you do not have to constantly reload the database. Where remote persistent memory, RPM, comes into play is for scaling the capacity of an in-memory application across a cluster of machines, so you can work on even larger data sets than you could do in one box. Of course, there are other applications able to take advantage of RPM. Software-defined storage, or SDS, more acronyms. A cluster of commodity servers loaded with storage. A cluster of commodity servers loaded with storage running software that pools the storage and provides storage features to the users. Think technologies like Ceph, except with RPM at much higher performance levels. Another one is big data. Hadoop, except with persistent memory instead of hard drives or SSDs. Machine learning clusters with persistent memory instead of SSDs. HCI, or hyperconverged infrastructure. With HCI, SDS, or software-defined storage applications, are running on VMs on the same nodes in the cluster as the user applications on other VMs. The application performance is best when the storage is local, of course, but this is often not the case. And writes to storage need to be replicated anyway, remotely, even if the storage is local. What RPM will do is greatly accelerate this and allow HCI to host much higher performance applications. All these and many other applications that rely on network storage will be able to greatly improve their performance with RPM. But there are also applications, or in this case, entire compute architectures that are enabled by RPM. The one I am showing now is compute disaggregation, not compute storage disaggregation, but 100% compute disaggregation. This is a concept that has been around for many years and was promoted early on by the Open Compute Project, or OCP, where CPU, memory, storage, and the network are all independent of each other. OCP laid this out in 3 stages, starting with the rack and then moving to the network within that rack, and they achieved the first 2 stages. And with NVMe over fabrics, is actually enabling effective compute storage disaggregation because of its near local disk performance, but across the network. RPM, assuming near local persistent memory performance across a network, assuming we can get there, enables the final solution to this disaggregation. So not only can the storage be disaggregated, but also at least a capacity tier of the memory. So those are some existing applications that can take advantage of RPM and a totally new architecture that is enabled by RPM. I'm also sure that RPM is going to enable the invention of many others. So how do we get there? Tony's going to go into the details, but here are some of the fundamental requirements. First of all, as I said earlier, persistent memory is very fast. So we need a very low latency network. And it also needs to have very high bandwidth. So we need very efficient protocol, and it needs to be offloaded into the hardware. I think the protocol to use is RDMA, and Tony's going to show you why in the next few slides. And we are talking about memory accesses, so the latency also needs to be predictable, not only fast, but also predictable and consistent, which means we can't have a network that is unreliable, for example, dropping packets. And we need to make sure that all the components in the network, whether it's switches, adapters, cables, etc., support these requirements. And with that, I will turn this over to Tony to dive into more of the details.
Rob, thank you very much. Before we go over to Tony, let me just remind the audience that if you have any questions at any time, please be sure to ask them using the online question window. We will answer all questions either live in the webcast or published in an FAQ about a week after the webcast published on the SNIA website. So Rob, great job. And with that, let's turn it back over to Tony.
All right, thanks, John. This is Tony Herson with Intel Corporation. I want to focus on the need for extensions to the existing RDMA protocols to really support this new networked persistent memory world very efficiently. And then I'll go into the first level of detail on what those extensions are. First of all, this is a slide that shows who is working on these RDMA extensions. There are three main flavors of RDMA in mainstream data centers today. Native InfiniBand, its InfiniBand over Ethernet variant, which is known as RDMA over Converged Ethernet, or RoCE, and then iWarp, which is RDMA over TCP, and the relevant standards bodies for those three are the InfiniBand Trade Association and the Internet Engineering Task Force. If you have a look at the emerging standards from both of those organizations, you may be confused a little bit by different names and terminology for these extensions. Thus, the IETF commit message that is new is known as a flush message in the IBTA emerging standard. And likewise, the atomic write new message is known as a non-posted write in IBTA land. However, a strong point to make is that the semantics, the functionality, the meaning of these new messages and modes are similar, such that we continue this beautiful world that all those flavors of RDMA have a single verbs interface, which is the recipe for application programming interface developers to write their APIs to, such that a single application can be written and run over any of these fabrics. We want to continue that, beautiful regime. Okay, I'm going to talk about how we need a small number of extensions to RDMA to really use networked persistent memory to its full potential. Rob showed us that it is at least an order of magnitude faster than the current fastest non-volatile technology, solid-state disks or SSDs. But we want to make sure that from a network protocol standpoint and at the application level assurance standpoint, that the network behavior with RDMA matches that huge latency speed up. I've got a couple of examples of applications using remote persistent memory to talk through the need for specific new features in RDMA. The first one is probably the most common we can think of when we talk about networked remote persistent memory. This is a high-performance database application, and it's also a highly available one, so the relevant persistent memory where change records are stored in persistent memory, that persistence is replicated for availability reasons. So there's no single point of failure. So that's the reason why this application is networked to multiple servers that you see on the right-hand side. In this particular example, we have a database writing to its update log. The story with databases are if they change records, they want to write the change information to the fastest possible persistent storage, which up until now has been solid-state disks, and now is this byte-addressable persistent memory. So they want to write that and get confirmation of the write, and then they can move on to the next transaction. So it's very latency critical, and we want a network protocol to match the potential huge latency benefit of this new persistent memory type. A level of detail here is that the database write log is organized as a circular buffer, or a first in, first out FIFO buffer. It is persistent though. If the server crashes or it powers down, we expect the data to be retained, and we're absolutely reliant on that across these two replicated server nodes. So some of the next level of detail of that circular buffer is that it obviously has data records. You know, typically for databases, those are 4 kilobyte each. And then we need to update the write pointer that points to the next empty location in that circular or FIFO buffer. In this case, implementation-wise, the persistent memory is sitting in a non-volatile dual inline memory module, basically a memory stick, that is plugged into the server CPU's memory socket. So it may take up say a single socket in that server's DRAM sockets. And one point to make here quickly is that the ordering of the writes here of the actual log data, followed by the write pointer update, is pretty essential. Otherwise, you get data consistency issues at the server, and you may corrupt the data. But I'll go into that in more detail in an upcoming foil. The second application I want to bring up is hot tier storage in a data center. It's an interesting one, and I created this foil because it's a different form factor for the non-volatile memory sitting in the target node, in this case compute node 1. Because this time we're going to park the bulk data persistently in the persistent memory region, or PMR, of a non-volatile memory express, or NVMe, solid-state disk. So this is a plug-in solid-state disk. And that emerging standard for an optional PMR buffer within an SSD, it's still in development within the NVMe Association, is basically a chunk of general purpose scratchpad memory, probably in the gigabytes to low tens of gigabytes. And the novelty is that it is persistent, right? So if the lights go out in that compute node 1 and you've written data to that PMR, it will persist and will be there after the compute node 1 powers up and recovers. This is a great application for either the hyperscale or hyperconverged variants of hot tier storage, two very common applications in data centers today. Why? Because the profile of the replication that is going on here of storage data is that it's latency critical. The compute node 0, its application, if it's a synchronous write, that application can't progress until that replica is confirmed persistent on compute node 1, the replica node. However, a very pertinent point number 2 is that the data, that replica on compute node 1, is hardly ever used. It's put there for availability reasons in the event of node 0 failure. And since time-wise that hardly ever happens, the vast majority of these replica writes are dumped in compute node 1 and they're never ever used. So they're sort of nuisance traffic in terms of useful work going on in compute node 1. Now, with PCI Express or PCIe I/O bus transfer, with peer-to-peer transfer between the RDMA network interface card, or RNIC, and the PMR-based SSD, the bulk data here of this transaction can go directly across the PCI Express I/O bus in peer-to-peer fashion between the network card and the SSD without pestering the target node's CPU memory system whatsoever. It reduces that huge bandwidth load from the CPU subsystem of that target server. So a very, very attractive mechanism for this hot tier application. Quite often there is also metadata accompanying the actual disk application storage data itself, and there its location is a judgment call as to whether compute node 1, the target, is going to actively process that metadata or not. As I show in the diagram, if it does process that metadata at the target node 1, it would pay to put that data in a persistent memory NVDIMM up close to the CPU that is going to use it. Otherwise, that metadata can be dumped in the PMR of the SSD just like the bulk data. Okay, now on to the extensions themselves. This slide tries to explain why simple RDMA writes, as they stand, are not enough, that we need to add extension messages to guarantee the persistence. And what it comes down to is that when an RDMA write completes at the originating node, in this case the client, when it completes at that client, that is no guarantee, as it stands, that the actual data has made it to persistence on the remote server machine. And I've tried to show that in exaggerated fashion here. I show a race hazard here where the RNIC, when it receives the RDMA write, it validates it and makes sure that it's legitimate in terms of placement. It validates it, and when it gets a positive indication there, it issues an acknowledgement, or ACK, back to the remote client machine. That ACK coming back completes that simple RDMA write operation at the client. But that action there and the behavior inside the server RNIC and the timing of that ACK is such that the client better not take the completion of that simple write as an indication that that data it has written has actually reached persistence. And I've shown inside the server that the write data sort of wending its way through the server subsystems, including volatile buffers in a PCI Express switch, which may be part of the I/O fabric, through the CPU subsystem, and finally to its persistent landing buffer in the non-volatile DIMM memory stick. So there's a race hazard here. It would be bad news if the client took that write completion to assume that all was well and the write is persistent, and then suddenly the lights went off in the server. So what we need extension-wise is an explicit, efficient confirmation of persistence to follow this dumb, plain RDMA write. Okay, so aside from the confirmation, explicit confirmation of persistence at the remote target node or server, there is a case in some of these applications that the succession of writes to persistent memory need to be ordered at their destination. They need to land in the actual persistent memories in a specific order. Otherwise, you get, again, in a situation where the server fails, you'll end up with data consistency issues. So here's an example. It's a slightly exaggerated example of a two-socket server system. It's quite a common server configuration. And it's back to my first example application, that database writing to the tail of its FIFO-based log. As you recall, the remote client first of all writes data in RDMA write number 1, followed by the write pointer update that moves the write pointer of that FIFO onwards. From a system level point of view, these writes need to be in that order, 1, 2, of data followed by pointer in terms of reaching persistence. And I've shown an example of a race hazard here, where it just so happened in the general purpose server, where, you know, an application has no control over where its persistent memory is going to be physically allocated. It just happens that the data region of the FIFO was in the far CPU socket with respect to the server's network interface card, RNIC, and the tail pointer is much closer to the RNIC. And so you can imagine, sort of visually here, it's quite easy to have a race hazard such that those two writes that start off in order in the network from the remote client end up out of order in terms of which one reaches persistence first. And if the tail pointer reaches persistence first before the FIFO data is written, and that server crashes or power fails, then you're going to end up with a nasty data consistency issue. I hasten to add is you don't need two-socket servers to do this. Anywhere where you have the server's persistent memory is physically distributed, as in multiple DIMM sticks within a single socket server, you're going to have this issue. Okay, so with those issues, those challenges in mind, confirmation of persistence and ordering of certain writes to persistent memory, the standard organization has come up with 3 new RDMA messages. I'm using IETF terminology here, but the IBTA specification has the same messages, just slightly different names. The first one is a commit request and response pair. So the client application does its write, and then it specifically launches a commit request in the tail of that write onto the network and says, hey, I've just written to memory region on server X of length Y, please explicitly tell me when that memory region, that write up ahead of it, has reached persistence. So the returning response from the server is the guarantee to that client application over the network that its specific RDMA write or writes to a specific memory region, persistent memory region that it owns on the server, has reached persistence. The second message is an atomic write request pair. And that one is quite small, less than or equal to 8 bytes, basically a pointer's worth of size restriction. And the atomic part of that write is that it's an all or nothing affair. In other words, going back to my application, the write pointer either occurs completely or that 8-byte write does not occur whatsoever in the event of server failure. And it again has an explicit response back across the network to the remote client that initiated it. And furthermore, that atomic write, if you look at its execution inside the server's RNIC, the write is held up from an ordering standpoint until earlier writes and commit requests on that same queue pair or connection have been completed at the server RNIC. So that's a way of having the server RNIC force ordering of that crucial follow-up 8-byte or less write. A third pair of messages, request-response pair, is a verify message. And right now that is only in the IETF standard. And it's meant for data paranoid, I would call them, applications, where the client writes data, it uses commits and or atomic write instructions to guarantee persistence and ordering. And even after that, it may additionally say, effectively, to the server, read back that memory, that persistent memory that I've just written in this range, address range, compute its hash, and compare it with this expected hash that I'm going to give you. And that's obviously a data integrity check that not only has the data reached persistence on the target server, but also that from a data standpoint, the data is good, is whole. Coming along
Tony,
with these, excuse me?
Tony, let me interrupt. Before you finish the slide, actually there's a question related to one of the, question or two on things you talked about. So the first question is, does this one still have the current RDMA write ACK or acknowledgement? I believe the question is about the atomic write request. Does that write request include the RDMA ACK?
It includes an explicit, the response is not a conventional RDMA transport layer ACK, which is a layer 4, a transport layer equivalent. This is an explicit new acknowledgement or response just for that atomic write request. The atomic write request, in terms of the request's format, is very similar to a plain write in the sense that it comprises a key, a protection key, a virtual address, and a length, in this case restricted to 8 or less bytes. So it looks, in that respect, it looks somewhat like a plain write, but you can clearly see in terms of behavior of the target, the responder RNIC, when it gets one of these, its behavior is quite different from an ordering enforcement standpoint, and also it has an explicit new response message with a new opcode coming back to the remote client.
Okay, very good. That makes sense. And one more question before I ask you to continue. The question is, why do we need a confirmation of rights at all? Why is it not sufficient to just have ordering or enforced ordering? Why do we need a confirmation of rights?
Okay, that's a good question. So I'll back up to that relevant foil. Yes, it's this one here. Why simple rights are not enough. This shows the green arrows show the entire pathway of a simple RDMA write, and specifically what happens to it when it reaches the server. Inside the server's RDMA network interface card, or RNIC, that write is going to be acknowledged as soon as it's validated. You know, we do all sorts of packet checks, stateless and stateful. We check its permission to write to that particular memory region on the server. But when the RNIC says all is well with this write, it positively acts it across the network. That write has not at that point reached its final persistent memory, which is the NVDIMM on the left-hand side of the server box. It still has to go through volatile buffers in the RNIC itself, a PCI switch if there is one, and the CPU, the main CPU chip. So there is a race hazard here that that ACK for the simple write goes back to the client and completes that simple write at the client, potentially before that data has actually reached persistence on the server. And it's to cover that race hazard window that we have invented an explicit commit, request, and response additional message pair that follows the RDMA write on the network to explicitly confirm that that write to that particular memory region has actually made it home to persistent memory.
Tony, that makes sense. Thank you for, I guess, reiterating that. If you could go back to where you were and continue, that would be great.
Sure. Okay, I was just going through, I think I covered the 3 new RDMA messages that will be showing up in all the transport protocols. Obviously, to distinguish these persistent data writes in the server, the target CPU subsystem, we need a new persistence property for the RDMA memory regions. You know, with plain vanilla RDMA applications, the story here is that the server exposes little apertures of its memory to a remote client. In this case, those memory regions that are exposed, explicitly exposed, will have a new persistence property. And that property is mainly to guide the target or server RNIC and also the server CPU subsystem, that for all the writes that are moving through from RNIC to the target server-based persistent memory, that this is persistent data traffic. So in terms of the commit operation, in terms of guaranteeing that it's reached persistence, this property is used by those server subsystems to guarantee that, to confirm that persistence. And then there will be, associated with that persistence property and these new RDMA messages, you'll see extensions to the existing verbs specification as written in the IBTA standards body for these new messages in memory regions. Okay, I think this is my last slide. How are we doing for time? It shows it shows timing diagrams between the client and server with these remote persistent writes. The left side shows the best possible scenario from a latency standpoint of achieving a remote persistent write with existing technology. And then on the right-hand side, the green ladder diagram, the new world, shows the use of these new commit and atomic write requests to guarantee persistence and to order certain writes to the same. The best we can do in today's systems is to guarantee persistence and ordering is that the client will issue a write the data value. And by the way, this example here that I'm showing is our old database example of writing FIFO data followed by a pointer update. The main inefficiency of the first one is that over in the client must stall its write pointer update until a previous read of the data, all of the data, come all the way back from the server, completes at the client. And what you may get there is 2 round trip times in the network. So even though the new world looks quite busy here with the new commit and atomic messages, it looks as busy or perhaps even busier than the existing world. It's much faster because if you stir hard enough and look at the triangles of interactions between the client and the server, there is 1 network round trip time here because all these operations, the write of data, the commit request issue, the atomic write of the pointer update, they're all pipelined by the client. They can issue them right at one after each other and not wait for responses. You can see here in this new world, you can see how in the server RNIC or interface card, the network interface card, it deliberately stalls execution of the atomic write until earlier commits on that same connection have returned and confirmed persistence of prior writes. So that's how we force that FIFO data followed by FIFO pointer example. We enforce that ordering at the server RNIC. Okay, and a quick foil that shows that even though IBTA and IETF are writing the RDMA specific extensions for remote persistent memory, we owe a debt of gratitude to SNIA, who was the first mover in coming up with a non-volatile memory programming model. And this is just a slide that shows how that the actions defined in that SNIA model of mapping the memory, syncing writes to persistent memory, and then finally unmapping or deregistering the memory, how that has echoed through into these RDMA network standards. And with that, I will hand off back to Rob to talk about some data results.
Thank you, Tony. Lastly, we want to tell you about a real-life demo of RPM. This demo was done at a past SNW conference, and no, it wasn't the SNW where the demo floor caught on fire. This was back in 2015, before HGST was part of WDC. My company worked with the HGST research team on this demo. We were providing the network equipment, which was 100 gigabit InfiniBand, the latest and greatest speed at that time. And HGST built prototype hardware to offload the network adapter to persistent memory interface, which was across a PCIe bus. The HGST persistent memory was called phase change memory technology, was based on phase change memory technology. That's why you see the PCM acronym. One more acronym for you guys. This diagram shows the topology of that demonstration. Standard RDMA read and write commands were used to access that persistent memory across the network. And the idea was to compare DRAM access to remote persistent memory access running an application, not just a test tool. So that was the background of the demonstration. What we showed was that even though DRAM access was faster than the persistent memory, once you measured it from the perspective of the application. So on the left side of this chart, you can see the difference in the persistent memory versus the DRAM access time. But what you see on the right side is that once you measured it from the perspective of the application, not just the test tool, the difference was in the noise. It wasn't measurable. So the purple is showing the persistent memory, and the green is showing the DRAM. And when you ran the application, the accesses, overlaid each other. So it really wasn't measurable, any difference between running remotely over persistent memory or locally on DRAM. So we believe, so this leads us to believe that we're, in the right ballpark here. That the tweaks to RDMA that Tony described, that the new model for applications for persistent memory that SNIA has done, that based on these, that we can meet the requirements necessary to implement RPM, or remote persistent memory. And with that, we'll enable all the applications that I talked about earlier and the invention of new applications of RPM to come. And that is the end of our presentation. John, I'll turn it back over to you.
Thank you, Rob. So we're going to take a few questions for Rob and for Tony. But first, I want to ask all our listeners that when you're done listening, please rate this webcast in BrightTalk. Give us your feedback, what worked, what didn't work, how could it be made better. But please let us know what you think. This webcast and a PDF of the slides will be posted to the SNIA Networking Storage Forum and available on demand. So you'll be able to download the slides as a PDF as well as watch a replay of the webcast. Any questions we don't answer here live will be posted in FAQ, or in a FAQ in a blog format on the SNIA NSF blog site. So you can also follow us on Twitter at SNIA NSF for the latest updates. So with that said, let's get to some of the questions here. And let me take a look. And so one question is, how is remote persistent memory presented to the client host? Meaning, how does the client see that RPM? So I guess either Rob or Tony. Tony, can you take that one?
Yes. Just like vanilla volatile memory applications, how the server, in the case of our talk here today, exposes its memory to the remote client is an application level handshake. So those two applications would, at connection setup time, typically chat with each other using send-receive messages, and the server would first of all register or map its remote persistent memory, however many gigabytes it needs, and would get the details back of that memory region in terms of a protection key, a virtual address, and a length. And the novelty is that that server application asks for remote persistent memory, and then it simply pops those details in a send-receive message, shoves it over the wire to the client in an application-specific way, and thereafter that client essentially owns that remote persistent memory from a writing perspective. That FIFO, in my first example, becomes owned remotely by the client application.
Okay, very good. Thank you, Tony. Now a question for Rob. Rob, the question is, what about the future of NVMe over TCP, which is something that is not yet standardized, but we hear the standard is getting close. Would this be much simpler for people to implement, and is it a good option instead of using RDMA?
So NVMe over TCP is a very interesting technology, and at Mellanox we support it fully across our product line. But if you remember back to when I was talking about the core requirements for network persistent memory, one of them was our ultra low latency networking. And although NVMe over TCP does have high bandwidth, will definitely have high bandwidth, at least the early testing we've done doesn't show that it has the kind of latency requirements that we were talking about. And also, another one of the requirements is predictability, zero packet loss. You know, we're talking about memory accesses here, so when you throw TCP IP's recovery mechanisms and, you know, one of its congestion management technologies that it uses or techniques that it uses for solving that is to throw away packets. So those sort of things are going to be very hard for a persistent memory, remote persistent memory connection to handle.
That's a good point, Rob. So while NVMe over TCP is coming, it's possible that it may not meet the performance expectations that some people have for remote persistent memory.
Exactly. It'll be good for many applications, but probably not persistent memory.
Okay. And I think another question, I think going back to Tony, and that question is, what is the time frame for these new RDMA messages to be available in the Verbs API?
Okay. Well, both the InfiniBand Trade Association, IBTA, and the Internet Engineering Task Force, IETF, they are shooting for the drafts of these new extensions to be out and in review by the end of this year. After that, you know, both of those organizations have different procedures for taking it all the way to making it an official standard, and I'd suggest that the questioner contact those trade associations to get detail of the timeline to full implementation. But the drafts are coming along well and will be out by the end of this year.
And I would add to that, like we talked about NVMe over TCP a minute ago, that standard isn't done yet, but there's plenty of implementations already, pre-standard implementations. So at a certain point, a standard is close enough to release to where you can start to implement. So I think you won't have to wait the entire standards process before you're going to start to see these, you know, at least pre-standard versions of the applications we talked about running with remote persistent memory.
And a related question to that, I don't know if it's from the same, coming from the same viewer, but where could I find more details about these 3 new verbs, and what are the arguments for those verbs? Do I have to wait for them to be published, or can I find out about them from either the IBTA or the IETF?
Join those organizations, and you'll be able to work on those standards along with the rest of the team.
All right, very good.
Tony, you want to add to that?
No. As I said, the drafts will be out by the end of this year. I know for the IETF, that means that they are going to be publicly available. You don't have to be a member of the working group or anything like that. But yeah, the best thing is to come join us and critique and make these things better and make them very robust.
For those of you who haven't been in one of these organizations, once the draft specification is put out, and then there's a comment period where anybody can ask questions, make comments, make suggestions to improvements.
All right, another question. We are starting to run out of time here. We can probably fit in 1 or 2 more questions. This is, and I think this is, Tony, addressing the part where you were talking about the acknowledgments from the write acknowledgments or the confirmation of the of data commit or flush. Where are these messages? Are these messages being generated from? Does the NIC know when the data has been flushed or committed? And either of you can take that.
So the new commit message will, over on the client side, will be basically the RDMA implementation of the SNIA persistent memory sync, or I believe there's an optimized action there as well. So they'll be packaged in a a function call for that client application that is using it to guarantee persistence. Over at the server RNIC, the execution of that incoming commit request is basically as follows. It will issue a 0-byte it'll issue an n-byte read request to the server CPU subsystem, and the PCI Express sideband signals like steering tag and protocol hints will be encoded properly to say this is to remote persistent memory, and that will key the target CPU subsystem in the server to search all of its pending write buffers, and if necessary all of its caches, if that persistent memory is cacheable, and will chase that data, pending write data to persistent memory. It will chase it out to persistence before returning that PCI Express response to the RNIC. So that's how the server-side RNIC gets confirmation of persistence.
Excellent, Tony. I appreciate that. So we're just about out of time. So we do have a few other questions that we haven't had a chance to get to. We will answer all those other questions in the blog and as FAQ or the Q&A blog. So don't despair. We will get to those questions as well. It usually takes us about a week to get that published after the webcast. Again, a reminder, the webcast is recorded. A recording will be available along with the slides, I think immediately following this webcast. You can go to the SNIA-NSF site to find it. Also, please do give us a rating. I see we've gotten some audience feedback and ratings already, so please continue that before you go. And I would just want to close with saying thank you, Rob. Thank you, Tony. This is an exciting topic. You know, I was just at the SNIA Storage Developer Conference. I'm sorry, I briefly stopped by the SNIA Storage Developer Conference, and I was also at Storage Visions earlier this week. And in both cases, I think SNIA has a demo of persistent memory. So this technology is here. You know, it's relatively new, but they have a server out there. They were showing a server, I think, with 3 different kinds of persistent memory, 3 or 4, running in that server. And so this technology is here, and it's going to definitely change some applications. It may not be used for everything, but it's going to change some of these applications and how people store, especially now, as Rob mentioned at the beginning, there's the option to treat it as storage over the PCI bus or as memory, depending on your needs. So except it's memory that's persistent. It remembers what you wrote to it, even if the power goes out. So any last words, Rob and Tony, before we close out the webcast?
No, but thank you very much, John, and thank you, SNIA, for the opportunity to present. It is, as John said, a very exciting time in the networking space.
Okay, Tony, any final words?
No. Thanks to everyone for listening, and thanks for SNIA and Bright Talk for hosting.
All right, with that, we will end the webcast. And just a reminder, you can find our other webcasts on the SNIA website. We have a bunch of other interesting webcasts that are related. We have the Great Debate series, as well as the Everything You Want to Know But Were Too Shy to Ask. And in addition to all our webcasts that you can watch on demand, the SNIA Persistent Memory Summit is coming up in late January of 2019. So keep that on your calendars as well. Thank you, everyone. This is John Kim signing off for the SNIA-NSF, and we look forward to seeing you on the next webcast.